Example 7, blood flow. When we consider the flow of blood through a blood vessel, such as a vein or artery, we can model the shape of the blood vessel by a cylindrical tube with radius r and length L, as illustrated in figure 8. So there's r, and there's your radius r, and then your lowercase r here, and then we have our length L. Now, because of friction at the walls of the tube, the velocity v of the blood is greatest along the central axis of the tube and decreases as the distance r from the axis increases until the velocity becomes 0 at the wall. Now, the relationship between v and r is given by the law of laminar flow, discovered by the French physician Jean-Louis Marie Pouillet in 1840. And this law states that, for definition number 1, the velocity v is equal to the pressure P divided by 4 times the viscosity times the length times the radius r squared minus lowercase r squared. Now, the symbol for viscosity is the Greek letter eta, which is sort of like an N. And that is the viscosity of the blood. P is the pressure difference between the ends of the tube. And if P and L are constant, then V is a function of R with domain 0 to R. Now, the average rate of velocity as we move from R is equal to R1 outward to R is equal to R2 is given by the following. The change in V divided by the change in R is equal to V of R2 minus V of R1 over R2 minus R1. And if we let the change of R approach 0, we obtain the velocity gradient, and that is the instantaneous rate of change of velocity with respect to R. Now, the velocity gradient is equal to the limit as the change in R approaches 0 of the change in V over the change in R, which is equal to the derivative of V with respect to R. So what we want to do, okay, is we want to be able to take the derivative of this function. So we want to find the derivative of V with respect to R of the function, and let me use a bracket here, of the function P over 4 times R squared minus R squared. Okay, so what we want to do is take the derivative here. Okay, so the derivative means that we're going to have two things that we need to take a derivative of. So we want to take the derivative with respect to R of the following. And that's R squared. And then minus, if we distribute that, then we have lowercase r squared. Okay, so if we take the derivative of this first part according to R, well, this is all a constant, so therefore this is going to give us 0. Minus, if we take the derivative of R squared, well, that's going to give us 2RP over 4 eta and then times L. So therefore, if we simplify this a little further, then we are going to get the following. We're going to get negative PR, and the 2 over 4 becomes 1/2, so that's 2 and then L. So therefore, there is the derivative of our function. Okay. So now that we found the derivative, okay, now the next step is for one of the smaller human arteries, we can take eta, which is the n here, is equal to 0.027. R is equal to 0.008 centimeters. The length is equal to 2 centimeters. And the pressure is 4,000 dynes per centimeter squared. So what we're going to do is we want to be able to plug this into our function first. So by plugging it into the function, okay, we know that we have 4,000 over 4 times 0.027 times 2, and then we're going to multiply that by the value of r squared. So we're going to take 0.008 squared minus r squared. So using the calculator, we get the following. If we take 4,000 divided by 4 times 0.027 times 2, well, it's going to give us a value of approximately 1.85 times 10 to the 4th. And then here, 0.008 squared is the same thing as 6.4 times 10 to the negative 5th. Minus r squared. So now what we want to be able to do is we want to be able to then find that r is equal to 0.002 centimeters. The blood is flowing at a speed of what? So if we know that r represents 0.002, we're going to plug that in. So we have 1.85 times 10 to the 4th times 6.4 times 10 to the negative 5th minus 0.002 squared. And so if we wanted to then multiply this all out, we'd have 1.85 times 10 to the 4th times, if we move this decimal place to the right, then we would subtract 1, so we get 664 times 10 to the negative 6 minus, this would give us 4 times 10 to the negative 6. And so therefore, if we multiply this all out, what we end up getting is 1.11 centimeters per second. So this is the speed of the blood that it's flowing at, 1.11 centimeters per second. Now what we want to do is we want to find the velocity gradient at that point. And so we're going to use these values in addition to when r is equal to 0.02 to find out what is the velocity gradient, because now we're using the derivative function. So if we want to find dv over dr, we know what the derivative is, and we're going to plug in the value. So we know that p is 4,000 times r, which is 0.002, all over 2 times eta, which is 0.027, times the length, which is 2. And so that's going to give us approximately negative 74. In the numerator, we have centimeters per second divided by centimeters. So therefore, to get a feeling for what this statement means, let's change our units from centimeters to micrometers. 1 centimeter is equal to 10,000 micrometers. Then the radius of the artery is 80 micrometers. The velocity at the central axis is 11,850 micrometers per second, which decreases to 11,110 micrometers per second at a distance of when r is equal to 20 micrometers. The fact that we found the derivative of this function, that rate, was negative 74 micrometers per seconds per micrometers, means that when r is equal to 20 micrometers, the velocity is decreasing at a rate of about 74 micrometers per second for each micrometer that we proceed away from the center.